Welcome to AI Frontiers, where today's episode embarks on a comprehensive journey through the latest advances in information theory. This exploration is based on 15 select research papers submitted to the arXiv preprint server's cs.IT category between May 1st and May 15th, 2025. The aim is to unpack emerging trends, discoveries, and methodologies that are shaping the field, while translating complex research into engaging and accessible insights. This discussion is designed for both established researchers and those curious about the foundational mechanics behind our interconnected world. Throughout this episode, an evolving science will be traced, one that underpins the technologies driving communication, data processing, and networked intelligence. Listeners are invited to join as the boundaries of information theory are examined, focusing on breakthroughs, methodological innovations, and the future directions that are setting the agenda for information and communication technologies. To begin, it is important to orient within the landscape of information theory, often abbreviated as cs.IT in computer science. Information theory is a foundational discipline concerned with quantifying, representing, transmitting, and processing information. The origins of this field trace back to the pioneering work of Claude Shannon, who introduced the concept of measuring information in bits and established the mathematical limits for efficient and reliable communication, particularly in the presence of noise and errors. Over time, the scope of information theory has expanded far beyond its initial focus on telecommunications. Today, it provides the mathematical backbone for a diverse array of technologies, including wireless networks, cryptographic systems, data compression algorithms, and the design and training of modern artificial intelligence models. The influence of information theory now permeates digital infrastructure globally, supporting everything from deep space image transmission to the seamless operation of 5G and emerging 6G networks. Furthermore, the field increasingly intersects with areas such as quantum computing, computational neuroscience, and machine learning, reflecting its dynamic and interdisciplinary nature. The first key research theme centers on the integration of artificial intelligence and deep learning techniques into communication systems. Recent work, including that by Huang and colleagues, demonstrates that deep learning models significantly enhance channel state information feedback in multiple input, multiple output, or MIMO wireless systems. Additional studies, such as those by Smith and collaborators, utilize generative adversarial networks, commonly referred to as GANs, to probe and expose vulnerabilities in AI-driven communication architectures, especially under adversarial attack scenarios. Patel et al. Further explore the development of training 3 semantic communication techniques using diffusion models, which are designed to improve system adaptability in rapidly evolving environments. Across these efforts, artificial intelligence is being harnessed to optimize the physical communication layer, enabling smarter and more context-aware networks. This integration sets the stage for communication infrastructures that are not only technically advanced, but also highly responsive to real-world variability. A second prominent theme is the rise of semantic communication, representing a shift from traditional bit-based paradigms to those that prioritize the transmission of meaning. In this context, Golapur and colleagues have developed mathematical frameworks for quantifying semantic information, while Kim et al. Investigate encoding and decoding strategies that are robust to semantic ambiguity. The integration of semantic communication techniques into federated learning systems is also being explored, with the aim of ensuring that user intent and meaning are preserved during distributed learning processes. This shift reflects a fundamental change in perspective, moving from the mere transmission of raw data towards systems that guarantee the accurate interpretation of underlying intent. As a result, communication system design is being aligned more closely with the needs of both human users and intelligent agents, marking a significant step toward more effective and intuitive networked interactions. A third major theme highlights the advent of intelligent surfaces and adaptable network infrastructures. Research by Saif and colleagues demonstrates how the deployment of reconfigurable intelligent surfaces, or RIS, in conjunction with unmanned aerial vehicles, or UAVs, is facilitating the creation of dynamic and resilient wireless networks. These innovations include the partitioning of RIS and the clustering of users to enhance network connectivity, particularly in environments where traditional line-of-sight communication is obstructed. The resulting networks are capable of real-time adaptation to physical blockages and changing environmental conditions. Advances in optimization and signal processing underpin these developments, making them practical for deployment in emergency response scenarios, rural connectivity initiatives, and densely populated urban areas. The convergence of these technologies signals a new era in network topology, characterized by flexibility, robustness, and enhanced connectivity. The fourth theme focuses on the algorithmic and theoretical underpinnings that ensure the security, efficiency, and robustness of information transmission. Recent research includes improvements in unsourced random access schemes and the development of efficient decoding algorithms for complex communication channels, as exemplified by Lee and colleagues. Information theoretic analyses, such as those conducted by Zhang et al., guide the understanding of fundamental performance limits and system behaviors. Additionally, outlier hypothesis testing under distribution uncertainty is being addressed, which is crucial for achieving robust inference in distributed network environments. Collectively, these efforts tackle the challenges posed by adversarial and uncertain conditions, employing advanced mathematical tools to inform the design and optimization of practical communication systems. The interplay between rigorous theory and real-world application remains central to progress in this domain. A fifth theme underscores the critical importance of security and robustness within intelligent, interconnected networks. As artificial intelligence permeates communication infrastructures, new vulnerabilities are emerging. Recent investigations, such as those by Lee and colleagues, reveal that generative adversarial networks can be employed to launch sophisticated attacks on AI-enabled networks. Additional studies, including those by Chen and collaborators, analyze the impact of malicious RIS attacks on vehicular sensing systems, highlighting the need for robust defense mechanisms. The development of advanced coding schemes aimed at ensuring safety and reliability further reflects this focus. Both offensive and defensive strategies are being examined to address the multifaceted nature of security challenges. As a result, security considerations have become central to the design and operation of modern communication networks, particularly as AI technologies are integrated more deeply into their core functions. Key findings from these 15 research papers offer several notable breakthroughs and insights. Huang et al. Have demonstrated that high-fidelity digital twins are essential for achieving robust performance in AI-driven wireless communication systems, effectively bridging the gap between simulation and real-world deployment. Seif and colleagues report that the integration of RIS, non-orthogonal multiple access, and UAVs can result in connectivity improvements of up to 40% compared to traditional network approaches. Li et al. Highlight the need for advanced defensive measures, having shown that GAN-based adversarial attacks can compromise AI-driven networks with high efficacy. Golapur and collaborators provide evidence that the semantic capacity of a communication channel can, under certain conditions, exceed the classic Shannon capacity, thereby expanding the theoretical limits of information transmission. Additionally, innovative image transmission frameworks have been developed, enabling graceful degradation of image quality even under severe bandwidth constraints. Collectively, these findings reflect both the diversity and the depth of current research in information theory. The methodological innovations observed across these papers reveal several prevailing trends. Deep learning models, particularly those based on convolutional and generative neural networks, are widely used for channel feedback and adaptation, delivering strong performance in complex and variable environments. The deployment of digital twins, as highlighted by Huang et al., enables scalable and realistic training for AI models without the need for extensive real-world data collection. Optimization heuristics, such as those employed by Seif et al., facilitate efficient resource allocation in wireless networks through iterative and practical algorithms. Rigorous information theoretic analyses remain foundational, guiding the delineation of system limits and providing performance guarantees. Hierarchical federated learning approaches are also gaining traction, supporting privacy and scalability in distributed systems by enabling model training without centralizing sensitive data. These methodological choices underscore the field's commitment to both innovation and practical deployment. The closer examination of seminal contributions begins with the work of Huang and colleagues, who address the challenge of training data scarcity for AI-based channel state information, or CSI feedback, in MIMO wireless networks. Their study involves the construction of both a high-fidelity digital twin and a matching physical testbed, allowing for rigorous evaluation of deep learning models trained in simulated environments. The results reveal that, although online learning can enhance model performance during deployment, it cannot fully compensate for the limitations of poorly calibrated simulation data. High-fidelity digital twins are thus critical for ensuring that AI models generalize effectively to real-world conditions. This benchmark study sets a new standard for bridging the gap between simulation and operational deployment in wireless communications, offering practical guidance for researchers and practitioners seeking cost-effective and scalable AI-driven solutions. The second seminal contribution comes from Saif et al., who focus on the design of resilient UAV networks through the joint optimization of RIS partitioning and user clustering. Their approach leverages closed-form signal-to-interference plus noise ratio, or SINR, analysis in combination with iterative optimization techniques to maximize connectivity. The proposed framework achieves up to 40% improvement in network connectivity over previous methods, demonstrating both theoretical soundness and practical efficiency. This research provides a blueprint for constructing robust, adaptable wireless infrastructures, with particular relevance for emergency response, rural connectivity, and challenging urban environments. The computational efficiency and real-world applicability of their algorithms further underscore the practical impact of this work, positioning it as a reference point for future network design. The third seminal paper, authored by Golapur and colleagues, lays the mathematical foundations for semantic communication systems. By bridging philosophical conceptions of meaning with engineering formalism, the authors introduce a probabilistic framework that defines semantic capacity and establishes lower bounds under conditions of ambiguity. Their analysis demonstrates that semantic capacity can exceed the classical Shannon capacity when uncertainty in meaning is present, thus generalizing the theory to encompass both linguistic and non-linguistic communication scenarios. This work paves the way for meaning-first communication systems, where the goal shifts from merely transmitting data to reliably conveying intent and significance. The conceptual and mathematical clarity of this framework provides a foundation for future research and development in next-generation intelligent networks. Looking ahead, several future directions are emerging within information theory research. The continued advancement of high-fidelity digital twins promises to accelerate the rapid deployment and validation of AI-driven communication systems. Universal, training-free, generative communication schemes are being developed to adapt to unknown or dynamically changing environments, reducing reliance on extensive prior datasets. Deeper theoretical investigation into the limits of semantic and distributed learning is underway, with the goal of establishing new benchmarks for system performance and efficiency. Strengthening privacy, safety, and adversarial defenses remains a top priority as networks grow in complexity and interconnectivity. Finally, ongoing challenges related to scaling, energy efficiency, and interoperability must be addressed to ensure that these innovations can be adopted widely across diverse technological landscapes. The synthesis and review process for this presentation involved multiple advanced tools and expert oversight. Language modeling and structural organization were performed using GPT-4.1 by OpenAI, while text-to-speech capabilities were provided by Deepgram. Visual content accompanying this episode was generated using Grok. To ensure accuracy and clarity, all material underwent review by a human expert with domain knowledge. It should be noted, however, that despite these measures, the potential for oversight remains. Listeners are encouraged to consult the cited research works directly for in-depth details and comprehensive understanding. All references are provided to facilitate further exploration and independent study. This concludes today's exploration of breakthroughs and trends in information theory, presented by AI Frontiers. For continued access to research insights, subscribing to the AI Frontiers channel on YouTube is recommended. Regular updates cover the latest developments in artificial intelligence, information theory, and communication technologies. Thank you for joining in this examination of cutting-edge science. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.